Okay, so in this next topic, we're going to look at the rate of a reaction. And what we've been looking at prior is how particles exist as essentially circles, the particle model. And what we haven't done is looked at how those particles can interact with each other on a chemical level. Everything up to now has been physical. So diffusion, melting, evaporation, things like that, and about how the particle model can be used to explain those types of things. What we haven't yet looked at, and what we're going to develop over these clips, is how the reaction between one particle, we'll call it particle A, and another particle, so for argument's sake, particle B, is these are now two different particles and how they will come together to produce another particle, a product of a reaction. And we need to look at the physical processes that have to occur to this before we can then look in more detail about how chemically that occurs with things like movement of electrons and things like that, and then we can relate to electron configurations for simple reactions. So if we're going to take the reaction of, as we've got here, A plus B, and we'll just say it's going to produce a second product of a particle C, whatever particle C is, doesn't really matter. And we need to look at how this can occur. So there has to be, at some very basic level, A has to come towards particle B. And that is the fundamental basic of how particles have to react. In order for particle A to react with particle B, there has to be essentially a collision. If there is no collision between particle A and particle B, then particle A cannot react with particle B. There's no magic, there's no trickery here. There has to be a fundamental basic collision of particle A touching particle B. If that doesn't occur, the reaction won't happen. So we can then move that on to suggest that if particle A has to collide with particle B, then the speed at which particle A is able to react with particle B and subsequently produce particle C, the product, in order for that to proceed, the rate of that reaction, i.e. the number of particles that can collide per second, or the number of particles that can react per second, the rate is proportional to the number of collisions. Okay, so it's proportional to the number of collisions. So what we're going to do over these next few clips is look at how we can affect the number of collisions per second between particle A and particle B. And what we're going to look at is a number of different areas. We're going to look at surface area. So we'll look at a solid reaction with a liquid on top, a solution on top of it, so marble chips and hydrochloric acid, for example. We will then look at a solution reaction, so we'll look at the concentration effect of two solutions, and we can use we'll use a potassium permanganate experiment for that one, and then we can change the temperature. So we can affect how hot a reaction will be. And we can look at those three variables and see how in turn they can affect the rate of reaction. And to top it off as a last, we will also look at how to catalyze a reaction, and then we'll have a look at a few biological examples for that as to how they work, things such as enzymes and things like that. So we'll work through these. But ultimately, we have to remember at the base of all these, the rate of reaction, i.e. the number of reacting particles, the production of particle C, the rate, the speed at which that is produced, is related to the number of collisions per second.